Efficient high-speed computing, low power. Multiplier architecture using Vedic mathematics. For digital signal processing applications. Abstract DSP, digital signal processing, applications typically involve complicated mathematical operations to be performed repetitively on data samples with less delay and power consumption. Multiplication-based operations like multiply and accumulate, MAC, and inner products are few computationally aggressive arithmetic functions, CAAF, frequently contained in today's VLSI systems and DSP applications like FFT, Finite Impulse Response filters, etc. Design of a high-speed 4/8-bit Vedic multiplier based on the techniques of ancient Vedic mathematics is proposed in this manuscript. Vedic method of multiplication strikes a difference in the conventional method of multiplication. Verilog HDL is employed for designing the structural modules, while Xilinx ISE tool is used for validating the designs. Keywords: Vedic multiplier, fast binary multiplication, HDL simulation, synthesis. Introduction. Multipliers are the primary arithmetic operational units that determine the execution time in many digital signal/image processing, networking, and communication-based applications. For the past many decades, multiplier designs are revolving around parameters of consideration like high speed, low power consumption, regularity of layout, and hence less area or even combination of them, with trade-offs among them, thus paving to implement compact digital systems. Owing to these parameters, technological advancements are urging researchers to innovate novel multiplication algorithms based on various serial, parallel, and hybrid multiplication techniques. Although there exist several types of multiplication algorithms, we have chosen to implement a digital multiplier suitable for digital signal and image processing applications using Vedic mathematics based on the ensured guarantee of faster and accurate calculations by Vedic mathematics. In 20th century Vedic mathematics name is discovered, which is given to the ancient Indian system of mathematics. The system of Vedic mathematics was entirely based upon 16 sutras or word formulae and 13 sub-sutras 8-9. Vedic mathematics reduces the complex calculations that exist in conventional mathematics. Out of all the 16 sutras available in Vedic mathematics, only 2 of them are made use of in multiplication operations. They are Urdhva Sutra and Nikolam Sutra. Urdhva Sutra deals with vertical and crosswise, whereas Nikolam deals with all from 9 and last from 10. Techniques of Vedic mathematics for digital multiplication are quite different from conventional multiplication techniques. Octor et.al1 implemented fast n times n multiplier in Vedic mathematics using VHDL, as it gives effective utilization of structural method of modeling 1. B.D. Kumar et.al2 highlighted the efficiency of Vedic multiplication where the design complexity is drastically reduced, modularity greatly increased for inputs having large no of bits. H. Goyal et.al3 implemented fast multiplier based on Vedic mathematics using modified square root carry select adder. This method reduces the carry propagation delay. Since adders are main components used in multipliers, using fast adders definitely enhances the overall performance of Vedic multipliers. Various adder topologies like ripple carry adder, RCA, carry select adder, CSA, square root carry select adder, SQRT CSA, etc., are used to compare area, delay, and power for. Since squaring operation plays a vital role in high-speed applications, where the speed is a crucial performance characteristic, like animation, digital signal processing, and image processing, etc. Yavadunam Sutra and bit reduction techniques are employed for squaring binary numbers in high-speed VLSI architecture 5. Multipliers employed in binary cubing architectures are designed using Anurupyana Sutra of Vedic mathematics. Combinational path delay is reduced and it achieves better area in terms of slices. Comparison is made between conventional and Vedic methods 6. These are faster than conventional square and cube because of its regular and parallel structure of Vedic square and cube. Because of reduced hardware complexity and delay, the proposed Vedic multipliers square and cube can be implemented in arithmetic and logic unit designs, replacing the traditional square and cube circuits 7. Most of the computing time is occupied by squaring operation, and it becomes to increase the speed which are to be squared. Remaining sections of the manuscript are organized as follows. Section 2 deals with different multiplication algorithms, and Section 3 deals with the proposed Vedic multiplication architecture. Experimental evaluations and analysis are depicted in Section 4, and Section V concludes the manuscript. 2 different multiplication algorithms. Multipliers play a prominent role in various digital signal/image processing, wireless communications, networking, embedded systems, and various applicable areas. The basic arithmetic operations addition and multiplication are fundamentally present in majority of the electronic circuits. Statistics clarify the facts that more than 70% instructions in microprocessors, and/or microcontrollers, and DSP algorithms include multipliers. Usage of multiplier circuits always compel designers to trade for added complexity and increased silicon area requirements with enhanced speed and power consumption, etc. Of course, there are numerous number of multipliers having unique pros and cons for themselves, which include the grid method, binary multiplier, shift and add multiplier, data multiplier, array multiplier, and sequential multiplier, etc. Few of the multiplication algorithms are discussed in this section. A grid multiplication algorithm. Grid multiplication algorithm represents an introductory method of multiple-digit multiplication. It remained a standard part of mathematics curriculum in England since late 1990s. Process includes partitioning the both factors to be multiplied into their hundreds, tens, and units parts. Further partial products are calculated explicitly in a simple multiplication-only stage, and these contributions are totaled to generate the final product in separate addition stage. For example, calculation of 34 times 13 is computed using the grid as shown in Fig 1. Fig 1, example for grid multiplication. Product is obtained through forming row by row totals, 300 plus 40 plus 90 plus 12 equals 340 plus 102 equals 442. B. Binary multiplication algorithm. Binary multiplication algorithm generates product of 2 binary numbers. Process includes calculating the partial products, shifting and adding them together. Long multiplicand is multiplied by 0 or 1, which is much easier than decimal multiplication, as product by 0 or 1 is 0 or same number respectively. Architecture 4. Fig 2, example for binary multiplication. C. Shift and add multiplication algorithm. Depending on the LSB bit value of multiplier, the multiplicand value is added and accumulated. For every clock cycle, the multiplier bits are shifted 1 bit to the right and its value is tested. If the multiplier bit is 0, then only a shift operation is performed. Similarly, if the multiplier bit is 1, then the multiplicand bits are added to the accumulator and resultant partial product is shifted to the right by 1 bit. After testing all multiplier bits, the product is retained in the accumulator. The accumulator is 2n, m and n, in size. This circuit carries several advantages in asynchronous circuits. Architecture for shift and add multiplication is shown in the figure. Point 3 below. D. Data multiplication algorithm. Data multiplication almost resembles the Wallace multiplication algorithm. Unlike the Wallace multipliers that perform many reductions on each layer, data multipliers do very few, minimum, reductions. Hence, data multipliers represent a less expensive reduction phase, while the numbers are a few bit longer, requiring slightly larger adder circuits. This implies that only fewer columns are compressed in the initial stages of the column compression tree, and more number of columns are compressed in later levels of the multiplication algorithm. Diagram representation of 8x8 data multiplier is shown in Fig 4. Below. Fig 4, example for data multiplication. A plain diagonal line connecting 2 dots in figure above represent the outputs of the full adder, while the outputs of half adder are represented by crossed diagonal lines connecting 2 dots. Array multiplication algorithm. Array multiplication algorithm represents an efficient layout of combinational multiplier design. Here the multiplication process is purely based on add and shift algorithm. Each of the partial products are generated through ascertaining product of multiplicand with 1 multiplier bit every time. Likewise N1, N denotes number of multiplier bits, number of adders are required to complete the process. Hence array multiplier is considered to consume more number of logic gates and hence occupy more area. Therefore array multiplier is economically less feasible, though it is faster in operation. 10 Architecture for array multiplication as shown in Fig 5. Fig 5, example for array multiplication. F sequential multiplication algorithm. Sequential multipliers are mostly preferred because of their low area requirements. A sequential multiplier multiplies two binary numbers, multiplicand xn bits and multiplier ym bits, using single n-bit adder. Firstly, the circuit processes a single partial product at once and it repeats the it to m times. Figure 6 below shows the partial product generation and addition in a sequential multiplier. Fig 6, example for sequential multiplication. Here the multiplication process is divided into some sequential steps such that in each step, the generated partial products are added to an accumulated partial sum. Further, the partial sum is shifted to align the accumulated sum with partial product in next steps. In every step, sequential multiplier includes three operations to generate partial products, adding partial products to the together partial sum, later shifting the partial sum. Therefore, every step in sequential multiplier includes three different operations of generating partial products, adding partial products to the accumulated partial sum and shifting the partial sum. 3. Proposed Vedic multiplication algorithm. The word Vedic is procured from the word Veda. The word Veda represents the storehouse of all knowledge. Vedic mathematics is a part of 4 Vedas, books of wisdom. It is a part of Sthapatya Veda, book on civil engineering and architecture, which is a Upa Veda, supplement, of Atharva Veda. Vedic mathematics can give a proper knowledge of several concepts in mathematics like arithmetic, geometry, trigonometry, factorization, calculus, quadratic equations. Jagadguru Shankaracharya Bharati Krishna Tirthaji Maharaja, 1884–1960, makes all part of the work together and gave a proper mathematical explanation which is useful for various applications. Swamiji constructed 16 sutras, formulae, and 16 Upa sutras, sub-formulae, after extensive research in Atharva Veda 7-8. These 16 sutras are dealing with various groups in mathematics like geometry, calculus, etc. These sutras are enlisted alphabetically, below, along with their brief meanings. 9. KalanakalanaBham differences and similarities. Ikadhikana Purvina increment 1 more than the previous one. Ikanyunna Purvina decrement 1 less than the previous one. Gunika Samakya factors of sum is equal to the sum of factors. Gunatasamachya product of sum is equal to the sum of product. Nikalam Navatashkaramam Dashata all from 9 and last from 10. Paravartya Ujayat transpose and adjust. Paranapuranabham by the completion or non-completion. Sankalanavaya Vakalanabhyam by addition and by subtraction. Shasanyankanacharmina remainders by the last digit. Shanyam Samyasamukhe when the sum is the same that sum is 0. Sopantadvayamantyam ultimate and twice the penultimate. Urdvatir Yagbhyam vertically and crosswise. Vyashtisamansta part and whole. Yavajanam whatever the extent of its deficiency. Fig 7, Architecture of Vedic multiplication. Architectural design of proposed Vedic multiplier is shown in Figure 7. Above. For 4-bit multiplication, input bits are divided in 2 equal parts, cross and vertical product computations are performed. Input data is A equals A3 A2 A1 A0 and B equals B3 B2 B1 B0, while the output bits represented by S equals S1 S2 S3 S4 S5 S6 S7 S8. Proposed architecture is comprised of designing different structural modules like A. 4 2-bit binary multipliers, B. 2 4-bit parallel adders, C. 1 2-bit parallel adder, D. 1/2 adder. Detailed operations relevant to structural details of above modules are elaborated below in a sequential manner. A. 2-bit binary multiplier. Design of 2-bit binary multiplier is meant for multiplying the two 2-bit binary numbers and provides the result. Methodology of multiplication is based on calculating the partial products, shifting them and adding them together. The logic diagram of 2-bit binary multiplier, as depicted below in Figure 8, contains two half-adders and AND gate units. Fig 8, logic diagram of 2-bit binary multiplier. 4 such 2-bit binary multiplier units are employed for the overall top-level design unit. B. 4-bit parallel adder. A full adder can take 3 inputs and performs addition operation with an input carry. But a parallel adder is a digital circuit, which is a cascade of several full adders. Such a n-bit adder formed by cascading n full adders, FA1 to FAN, is used to add 2 n-bit binary numbers. A ripple carry adder is a simple form of parallel adder, where the carry-out of each full adder is connected to the carry-in of the next full adder. Hence the total delay time of the adder is the time it would take for a carry to ripple through all bit pair full adders. Block diagram of a 4-bit parallel adder is shown in Figure 9 below. Fig 9, block diagram of 4-bit parallel adder. C. 2-bit parallel adder. A 2-bit parallel adder is designed using an XOR, exclusive OR, gate and AND gate. Here 2 full adders are connected in a parallel manner. The block diagram of 2-bit parallel adder is shown in Fig 10. The logic diagram of 2-bit parallel adder is shown in Figure 11 below. For experimental analysis, structural modules of proposed multiplier are designed using Verilog HDL programming language. The structural design modules are validated using Xilinx ISE tool. Experimental evaluations pertaining to the simulated waveforms and results obtained for various other blocks are critically evaluated below. Fig 13, simulation waveforms of 4-bit multiplier. Experimental analysis performed for 2-bit, 4-bit, 8-bit, and 16-bit multiplications. Simulations relevant for 4-bit Vedic multiplication operations corresponding to different 4-bit input values, A and B, are displayed in Figure 13. Similarly, waveforms relevant to 2-bit operations are shown in Figure 14. Below. D. Half-adder. Half-adder is constructed using an XOR gate and an AND gate. It is meant for adding 2 bits and generate a sum bit, S, and carry bit, C, as the outputs. Though half-adder is a simple circuit, it has a major disadvantage of adding only 2 input bits, A and B, and has nothing to do with the carry, if there is any in the input. That means the binary addition process is not complete and hence it is called a half-adder. Logic diagram of an half-adder circuit is shown in Figure 12. Below. The waveforms relevant to 4-bit parallel adder with inputs A3:0 and B3:0 generating 8-bit sum output and single-bit carry output is displayed in Figure 15. Below. Waveforms relevant to 2-bit parallel adder with inputs A1:0 and B1:0 generating 4-bit sum output and single-bit carry output is displayed in Figure 16. Below. V. Conclusion. With regards to operation of various multiplier circuits, parameters like operating speed, power consumption, and silicon area under usage are of primary concern, that are in turn dependent on the typical adder circuits deployed. Proposed Vedic mathematics binary multiplier circuits are explored with binary parallel adder circuit components. Here it is observed that parallel adders are more efficient in terms of operation. In contrast, carry increment adder circuits are meant for future deployment as they require only little additional logic and reduced delay at the cost of circuit area.